Nature Hacker, and this is your world. So, first today I want to talk about Newton's laws and rockets don't work in space, part 9. So, where I'm at in this, it's been a journey. I've gone through a lot of evidence and had lots of, I guess you could call them talking points as far as, explaining this to people. And what I'm really falling back on, not necessarily falling back, but falling into right now is the friction argument, which is just a natural progression of thinking about joule-free expansion and, forces involved and things like that. So I think the easiest way to explain this to people at this point is to primarily use the friction argument. And basically that is that in space, when a gas is exposed to a vacuum, there is no friction. There is no friction involved because the gas particles, they don't have to rub against the walls of the chamber or anything like that. They are just free to go in the direction of least resistance, which is out into space. And this is proven by really the Bernoulli principle that the gas will go around a body unless there's air resistance. Gas will just go around a body, and there can't be air resistance in a vacuum like space. So without air resistance, there is no friction. Okay, and if there's no friction, there can be no force. So that's why I want to talk about how Newton's laws are debunked. Okay, I'm debunking Newton's laws right now. And it's not necessarily that his laws don't ever work. But what I am saying is that they don't always work, okay? There are some contingencies, there are some presuppositions to Newton's laws, and Newton didn't know this. I mean, it's not Newton's fault. The only people whose fault it is the NASA believers for being, Newton is turning in his grave right now. I mean, he doesn't want his laws that he wrote to be taken out of context and just to be blindly followed by these followers of NASA. Literally, they're blindly following Newton's writings, and Newton's writings are outdated. Okay. So what are the contingencies of Newton's laws? What are the presuppositions? The presuppositions, contingencies are friction. Okay. So let's say you throw a ball, right? That's the classic example of Newton's laws in the minds of the NASA followers. Well, just try to throw a ball without friction. Try to cover that ball in oil, okay, and then try to throw it. Are you going to be able to throw the ball as far if it's covered in oil? No, you're not, because you can't grip it, right? You have to be able to grip the ball to throw it. And you could think of a medicine ball. Yeah, okay, you just push the ball, right? But if there's not friction, your hands would just slip off. I mean, literally, you would have to push it perfectly perpendicular. If there was zero friction, you would have to push it perfectly perpendicularly, like to the nano angstrom, okay? It's just like, that's impossible. There is no such thing as perfectly perpendicular. There's no such thing. There's no such thing as perfect. Okay, so you cannot push something with no friction. That is just the way it is, okay? So Newton's laws presuppose friction. And now that makes total sense with everything we've gone over in parts 1 through 8. Perfect sense, because it makes perfect sense with joule-free expansion, and the reason why a gas expands freely when exposed to a vacuum is because of there's no friction stopping it. It will expand freely because there is no friction. So I guess, and this is even my argument here is not perfectly correct. So I mean, that's why you should know that never take anything at face value. Never be a follower. Always think for yourself. Always continue to add on things. And it would do me injustice if you took what I said and you just blindly followed it for hundreds of years, like people have done Newton. So that would freak me the truck out, okay, if you just blindly followed everything I said, because then it's like your life is worthless, right? If you're just following what I say, then what value does your life have? You're just an extension of me, and that sucks, okay? So if you want to honor my memory, if we want to honor Newton's memory, we need to take what I say and we need to add on to it. We need to test it. We need to prove it. We need to continue to improve it, okay? Then that does my memory well. And it's the same with Newton. Take what he did, figure out exactly how and what it applies to, and continue improving his theory, okay? Now, I'm saying, what I just said is that Newton's laws require friction. That is not exactly correct, okay? There's something even more basic than friction, and that is constrained motion. The motion of the object that you are pushing, in a Newton's, I guess, third law. I mean, it's all of Newton's laws as far as Newton's second law and third law, F equals ma, and the equal and opposite forces cancel each other. So in order to create movement, and some people are like, oh, creating movement is not a force. A force is change in movement. Okay, well, same thing. Okay, same thing. Going from zero relative velocity to a greater relative velocity is change in motion, which is a force. So in order to apply a force to something, in order to change something's movement, to change something's velocity, you need to constrain its motion. You need to constrain its motion, okay? So, like, let's say that you want to disprove me that it requires friction to push something, right? Okay, so you're like, okay, well, here's the ball, right? Now, yeah, I would need friction to throw that ball because, my hand would just slip off without applying force to it, right? But you can come up with a counterexample of, well, what if I'm throwing the ball like this? I'm pushing this forward and that, and then releasing, and then the ball keeps going, right? You're disproving my theory that it requires friction. Yeah, and you did. You disproved my theory that it requires friction. However, the theory is more basic, more fundamental than friction, and that is the constrained motion. You're constraining the motion of this in this direction. You're constraining its motion in this direction. If it was a perfectly flat cup like this, and I'm going to push, it's going to slide off the side, right? I mean, and if it was like this, and I'm pushing, I mean, it's impossible to have a perfectly flat plane. So if I'm pushing, it's just going to slide off like this. It's just going to slide off. Just like, the Bernoulli principle of gas that goes around something. It goes around something if there is no air resistance. Okay? If there is air resistance, then it will get pulled off the back and it will apply a force in that pressure differential that it creates. What's happening is you have to constrain the motion in all three dimensions in order to apply a force. Okay, you can do that easiest with friction, so with some, frictional contact, and then you're constraining the motions. You're constraining the motion in three dimensions. Okay, so if you don't have friction, you still need. Gosh. Okay, so you still need to constrain the motion in 3 dimensions. So you're basically forcing the thing that you're applying a force to go in a certain direction. So that applies to Joule-free expansion, and this is how. In Joule-free expansion, or let's say in an underexpanded nozzle. In an underexpanded nozzle, the gas is coming out and it just goes out at like right angles. At a fully underexpanded nozzle, the gas exits in all directions. You know, it's just goes out in all directions, okay? Since you're not constraining the direction of motion, you cannot apply a force to the gas. Does that make sense? So when the atmospheric pressure around a rocket nozzle is very low, let's say near vacuum, the escaping gas just goes out in all directions, 360 degrees. So since you are not constraining the direction of motion, you cannot apply a force to the gas. Another way to think of it is that the center of mass of the gas doesn't change. Okay, if you can't apply a force to the gas, then the center of its mass won't change in position. Because in order to move the center of mass of a gas, you have to accelerate it by applying a force. Okay, so if you can't apply a force, you can't move the center of mass, and that makes sense because here's the center of mass of the gas right here, and it just goes in all directions. The center of mass of it doesn't move. Okay, and you could think of the center of mass being in here, wherever. It doesn't matter. It's just it goes out in all directions. Okay, in order to not have the center of mass change. The center of mass might change, from here to here or something, but that's negligible. Okay, it's the same in a Joule-free expansion experiment. You have 2 bulbs right here connected, and this one's total vacuum, this one's got the gas in it. You open up the valves and the gas freely expands to fill this. But yeah, I mean, the center of mass did change from there to there, so you get a teeny weeny bit of force, but in a perfect situation, a perfect Joule-free expansion situation, you would have a jar within a jar, so that the center of mass doesn't have to change. It freely expands into the bigger jar. So there's that. Now, so how a rocket does work is that its motion is constrained by the atmosphere. So in an underexpanded nozzle, it just goes out in all directions, right? But in an overexpanded or an optimally expanded nozzle, the stream comes out like this. Its motion is constrained in 3 dimensions. It's constrained to go along that path. Okay? And that is why Newton's laws work on rocket engines in the atmosphere, because it's the rocket gas is confined in 3 dimensions. And that is why you can apply a force to that gas. It's because of atmospheric pressure that stream is confined. Okay, if there was no pressure here, you can't hold the stream together. It would just go out in all directions, and you can't apply a force in that case. And you can't apply a force because you're not constraining the direction of motion. Like I said, you have to constrain the direction of motion to push something. If there's no friction, you have to constrain the direction of motion. Okay? I'm trying to really be cohesive here and not leave any room for doubts and things like that. So, what else? That's pretty much so. I guess this is going to be parts 9 and just don't work in space. Thanks for watching. I am the Nature Hacker. Go do work.